OSPF version 3 and IPv6. It's so much fun. I cut it into two parts. In our first part, we're going to focus on the logic and characteristics of OSPF version 3 for IPv6. In the second part, part 2 of 2, we'll jump into the actual configuration, verification, and troubleshooting of IPv6's OSPF. Let's begin with part 1. So let's take a look at some of the characteristics, starting with link state. What exactly is that? Well, there's two families, as you very well may know already, about routing protocols. We have distance vector and we have link state. And how do they work? Well, they're both set up to share routing information so that dynamically when routes change, interfaces come up, go down, we can share that information across the network so we don't have to manually configure everything. With distance vector, it's not too smart. With distance vector, we have R1, R2, and let's say we have R3, and they're all connected like this. And R3's got some other networks out here. Well, with distance vector routing protocols, the only thing that R1 knows is what R2 tells him. That's it. So if R2 is accurate or not accurate about the state of R3's networks and so forth, R1 has to trust that neighbor, and that's it. He doesn't have direct access to information from R3. Well, that's distance vector in a nutshell. Well, link state routing protocols like OSPF handle it differently. There's R1, R2, and R3. And what's going to happen, we have the same interfaces, for example. So what's going to happen with link state routing protocols is that R3 is going to generate an LSA, a link state advertisement. Guess what a link state advertisement is advertising? It's advertising things like the state of R3's links. And there's various types of LSAs, but the basic concept is we're advertising all the information about R3 and all the other routers across the entire network. So if these three devices are all in the same OSPF routing area, the LSAs from R3 are going to be sent to R2. R2 is going to be a good neighbor. He's going to make sure that R1 sees that. So now all three routers, 1, 2, and 3, have seen the details of this LSA. Now, R3 generated it. He really didn't need to see it himself, but all three routers have the exact same copy of that LSA. R1 generates LSAs. R2 generates LSAs. And at the end of the day, all these three routers, they know every single router's LSAs. They know all of the interfaces that are up, and then they can calculate based on all the information, straight from the horse's mouth, so to speak. They can calculate their own shortest path first to get to a given destination. And that's what they do. They take all the data they got, they take their current position in the network, and they calculate what's the best way to get to network X right there. And that's what a link state routing protocol does. Also, if there's a change, if this network goes away, R3 sends a new link state advertisement, an update, and that update gets propagated to all the other devices. So R1 says, oh, that network X is gone? Great. I'll take that out of my considerations. And if there is no other path to network X, we'll remove it from our routing table. A question that comes up all the time with OSPF, whether it's IP version 4 or IP version 6, is, well, what's the negatives of OSPF? Well, there's a little bit more to be aware of. There's more configuration involved for setting up large environments. And one of the problems is it takes a little bit more CPU because each device has to consider all the data for the entire network and then calculate their routes based on all that data. So what happens if you have a network with like 500 devices, 500 routers? So you got, I won't draw 500, but let's say you have a whole bunch. And if all of these devices are sharing all of their link state advertisements with everybody else, that means this router over here in Des Moines, Iowa, it loses one link, or a link goes down, and that update has to be propagated across the entire network, and everybody has to recalculate. It can take a lot of additional overhead in large networks. So here's what we do with OSPF. We'll take OSPF and we'll simply carve it up into smaller groups. That way, not everybody has to listen to all of the LSAs from everybody else. As an example, let's take R1, R2, R3, R4, R5, R6, and R7. Just a few routers there. And let's say they've got some basic connectivity. Maybe these guys are all connected to a switch here, and these guys are all connected to a switch here, and these guys are all connected here. So with this fairly simple topology, with 7 routers, that's no problem for OSPF. They could all handle the LSAs, and they could scale to larger than that. But as an example, if we wanted to optimize and take the CPU headache out of having to process every single device's LSAs, we could carve this up into logical areas. For example, maybe we take R1, and we put those interfaces from R1, R2, and R3 inside of an area. I mean, this is area 0. Sometimes it's called 0.0.0.0. It's really just a 32-bit number, and it's just really convenient in dotted decimal to represent 32 bits as 0.0.0.0. Either way, they call it the backbone area. And then we have maybe a second area over here that can involve these interfaces, and a third area that can involve these interfaces. And I'm being very careful to say that the OSPF includes interfaces, not really routers. See, a router can be connected to multiple areas inside of OSPF. It's the interfaces, one by one, that choose that we configure to belong to a certain area. So in this topology right here, if we take a look at it together, this interface on R2, this interface on R4, and this interface on R5 would all belong to this area. Let's call it area 45. So we have area 0 right here, and maybe this is area 67. And this interface is connected, this interface is connected, this interface is connected. And the beauty is that only routers connected to an area have to worry about the LSAs for that area. So as an example, R4, which a moment ago would have to process the LSAs for all of the other devices if it was one giant area. No, really, it just has to process the LSAs from R2 and from R5, and that's it. It doesn't have to worry about the LSAs from R1 or R3 or R6 or R7. And that's how we can organize a very large OSPF environment into smaller areas so that not every single device has to process the LSAs from every single other device. Now, there are some rules that we should definitely be aware of with OSPF. And one of those rules is every area has to be either the backbone or it has to be connected by a router that is connected to the backbone area. So if we take a look at this area right here, in fact, let me do this. Let me bring up a topology of pre-built, and we'll work from that going forward. So through the magic of Visio, let's use this topology. Here's area 0, here's area 45, here's area 67. Notice that this area 45 has at least one router that's also connected to the backbone area. And that's the rules in OSPF. Is you can't have an area, for example, let's say over here this was area 10. So area 10 doesn't have any routers that are also connected to the backbone. So that's the basic rule of OSPF, is that if you're going to have multiple areas, you can, but every area has to have at least one router in that area that's also connected to the backbone. The name of that would be an ABR, an area border router. Why? Because it's bordering two areas, the backbone on one side and some other non-backbone area on the other. R3 would also be an ABR, an area border router, because it's connected to area 67 and area 0. Now over here, area 67, and we have R7 that's connected to a non-OSPF routing domain. We call this guy an ASBR, an autonomous system boundary router. And good news, all of these concepts that we've talked about so far apply directly to both OSPF for IP version 4 and IP version 6. So if this was, for example, an OSPF area and we tried to set it up, we wouldn't have full reachability. It simply wouldn't work unless we got creative and started doing something called a virtual link to make a virtual path through this transit area so that R7 would believe he's connected to the backbone. We'll save those discussions for another day. However, the basics of OSPF in IPv6 work very similar as they do in IP version 4. Another common thing that both IP version 4 and IP version 6 have together is that they both require a router ID. Now, if you remember back to OSPF with IP version 4, how did a router determine its router ID? It had three basic things it checked. Number one, is it configured under router configuration? If not, what's my highest IP address on a loopback? If there are no loopbacks with IP addresses, it would then say, what's my highest IP address on any interface other than the loopbacks, which I didn't have any. That's the pecking order, 1, 2, and 3. Well, in IP version 6, it uses that same pecking order. However, it causes a problem in an IPv6 only network, because guess what? You may have router 9, and that router 9 may not have any IP version 4 addresses. So it can't pull one to use as a router ID, because a router ID is simply a 32-bit number. If you have any IP version 4 addresses configured, it will pull the highest one from a loopback. If no IP4 addresses are there, it'll pull the highest IP version 4 address from a physical or logical interface. If you don't have any there, it pops up a warning and says, sorry, There's no router ID. You can't find out what one is. Please configure one. So we're going to want to configure a router ID inside of OSPF, and it's going to look like an IP version 4 address, but it's really just 32 bits. So in R1, we could go into router configuration and say, I want the router ID to be 1.1.1.1. Or in router 2, I want the router ID to be 2222. Now, those aren't IP version 4 addresses as router IDs. They're just a 32-bit number that happens to be represented by 4 octets, which totals 32 bits. A couple other concepts that also apply to IP version 4 and IP version 6 are worth noting here, and one of those is an external route. Now let's say the R7 is an ASBR. Now, how do we know that? Well, because it's connected to OSPF and it's connected to RIP, next generation, and we're going to do some redistribution between the two. That's what makes this guy an autonomous system boundary router between a routing domain outside of OSPF. If we bring these routes into this area, R7 does, let's say this guy has a loopback of 888 or something. So the 8888 subnet is brought in through redistribution. It's going to show up as an external route from OSPF. It'll be a type E2. That's where whatever metric is set by R7 will stick with that route as it gets propagated through the domain. The 888 network will also show up over here as an external route, so this area and all the routers in it will know about it. If we don't want this area to have to worry and see about the external routes, we can make this area a stub area. And what a stub area says, it says, you know what, Mr. ABR, I want you to protect your area. Don't send any external routes. Just don't send them. So R2 will know about the 8888 network. However, he won't bother telling Area 45. But what he can do is, if configured to do so, he can provide a default route for these guys. So if they ever tried to get to a network 8888, at least they'd have some path to send the traffic to. So that's a stub area. Another option is a totally stubby area. And a totally stubby area is when we tell the ABR, hey, you know what? Don't even tell this area about networks from area 0 or other networks, including inter-area routes. Don't tell them anything. Just go ahead and send a default route so they can forward packets to get out of this area, and you'll be the ABR for them. So the concepts of backbone area, non-backbone area, stub area, and a totally stubby area, those concepts are similar to IPv4 and IPv6 with OSPF. Let's take a look at some of the details in our topology together. I've got this major network that we're working with, 2001 DB8 6783 and X. Now the X obviously is too high for a hexadecimal character. That goes A through F at the 10 through 15 range. But this X represents the actual subnet number. So to make it easier to work with, I just put the subnet in red, which represents that last 16 bits of the 64-bit network address space. So over here we have the 367 networks. All these guys are together here, and the 245, they're all together here. And then that guy's in his own 45A, 45B, 67A, and this is not running OSPF. This is a RIP next generation connection right there. Another common element between IP version 4's OSPF and IP version 6 is something called a DR. Doctor, give me the news. No, not that kind of doctor. The designated router. See, the concept is if we have like 5 or 6 routers and they're all connected to the same network, we really don't need to have every single one of those form a full formal adjacency with every other device. It's a lot of overhead that simply isn't needed. Instead, they can all agree that the designated router will be one device on that network. They can all form a formal adjacency with that DR, and for grins, we'll put a BDR there as well. So they can all form an adjacency with the backup designated router as well for fault tolerance. So that's a concept that's similar to IPv4 and IPv6 that we also should be aware of that it exists. And now it's time for everybody's favorite part of the game show called Name That LSA. And you're thinking, Keith, that's not my favorite part of the game show. Well, in either case, you and I definitely deserve to understand the details about the different types of LSAs that are out there in OSPF. Now, I talk about out there. That's how a lot of people think about LSAs. But if you break it down, what is an LSA? An LSA is a link state advertisement. It's some information regarding the state of one or more of our links. Maybe some of those LSAs have the actual IPv6 addresses associated with those. Maybe some of those LSAs describe the people who are connected to a broadcast network, multiple OSPF speakers. Let's do this. Let's do the old, and then we'll do the new. In the old world, in the world of IP version 4, just for a moment, let's take a look at the different types of LSAs. An LSA type 1 is a router LSA, and that is generated by every single router. So R3 is going to make one, R2 is going to make one, R4, R5, R6, R7. Everybody who's an OSPF speaker is going to generate an LSA type 1 in IP version 4. It basically says, hey, I'm a router, here's my router ID, and here are my links that I have. Great. The second type of LSA is a type 2, and that's not generated by every router. In fact, some networks may not even have a network type of 2 LSA, and that's because it's only generated by a DR, a designated router. So for example, let's pick R1. Let's say he won the election. He's the designated router for this segment. He will also generate a LSA type 2 to describe this network for which he is the designated router on. And in that information, it can also include things such as, here are the other people connected to this network. And that's what a type 2 LSA is all about. The next type is a type 3. Again, we're focusing just for a moment on OSPF version 2, which is IP version 4's flavor of it. If this was 3 areas as it's shown, and we have good old R4 here, I want to talk just for a moment about how R4 learns about subnet 67A. I mean, one of the benefits of carving up this big OSPF into areas was so that R4 didn't have to process the LSAs from area 0 or area 67 or other areas. And that's absolutely true. But at the same time, this router does need to know about reaching that network. So here's what happens. When this network hits this area border router, the area border router is not going to forward the link state advertisements from R6, the type 1 LSA that describe this network or anything else. It's going to simply say, you know what? I'm an area border router. I'm not supposed to forward link state advertisements for type 1s out of the area. So what I'm going to do is I'm going to convert that to a summary. When it says summary, sometimes I think, well, are we summarizing networks? Like we've got 17 networks. I want to summarize them to one network. Not that type of summary. It's a summary advertisement. It's a new type of LSA that's describing this network. So the LSA effectively would say something like this. It's an LSA type 3. And there's a network called 67A, that's the subnet from this full network. And if you need to reach it, by the way, because I'm the one that's advertising it, I'm your guy. So it's not a type 1 LSA that we're advertising over here about this network. It's a special type 3. They called it a summary LSA. The next piece that I'd like to go, I'm going to skip forward just for a moment. I'd like to go to LSA type 5. And LSA type 5 is this. Let's say that this router right here is RIP speaking RIP. And we're advertising networks into R7, and R7 is redistributing those from RIP into OSPF. That is now an external type 5 LSA. That's it. That's all it is. So that LSA gets advertised type 5 into this network. That would also show the advertising router who sourced that is R7. So this type 5 LSA is actually going to be forwarded through the entire autonomous system. So R4 down here is going to see this external route, that this LSA type 5 that describes the networks that are being redistributed. Let's say it's 8888, that subnet. So R4 will see 8888. It'll see it as an external type 2 by default with whatever metric R7 put on it, and he'll see it there, but it'll be an LSA type 5. Now there is a problem with that type of LSA, and that is it's going to describe the advertising router as R7. And the problem is R4 does not know about R7 over here, because R7 and his type 1 LSAs and what's describing him, those LSAs don't make it over to this area. So we need a little help. And that's why I did LSA type 5 first to describe the external network inside of OSPF. And the type 4 is to advertise how to get to R7. And so it's called the summary ASBR. And what will happen is this. R3, because he's a very diligent area border router, is going to say this. Okay, I just advertised an LSA type 5 about this external network. And I also know that the person who advertised that, R7, is in this area, and he's not in area 0. So what the area border router will do is he will advertise a type 4 summary And that summary ASBR is simply describing how to reach this guy. It's basically saying to the rest of the network, hey, you need to reach R7, go to R3. If you need to reach the external network, go to R7, which is reachable through R3. In a network where we haven't carved it up into multiple areas, it's just one area, and we have at least one broadcast domain with a couple routers, we're going to have LSA type 1s and LSA type 2s, and that's it. Once we start carving it up into areas, the area border routers are going to create our summary advertisements. If we're doing redistribution, at that point, we're going to see the summary ASBRs and also the external routes inside of our OSPF. Now, this last one right here is if you want this area to be a stub. So this is a stub area, but at the same time, you need a router in that area to redistribute into OSPF. To make that exception, they call it, well, it's a stub area. It's not really supposed to allow external LSAs, but let's do this. Let's make it a not so stubby area. And that's what a not so stubby area is all about. So if we wanted to, we could bring in this route as an LSA type 7, and that would be the case when we'd use the NSA external, is if we had a stub area, we need a redistribution, so we could make it a not so stubby area to allow that route to propagate through the network. And the concepts for that work the same in IP version 4 as they do with IP version 6. So now let's take what we know about IP version 4 LSA types and apply it to IP version 6. The first thing right off the bat we're going to notice is that there's more numbers. Are they hex? Yes, they are in hexadecimal. Now that means that what we're looking at really is 16 bits, every character representing 4 bits. But check this out. You don't need to take it to binary or anything else. You can just look at the first number and gather information from it. So this first number, we have 3 choices that are shown here. We've got 0, which is this guy. I've got a 2, which is this guy, this guy, this guy, this guy, this guy, and this guy. And I've got a 4, which is only this guy right there. And that first number, what that tells us right off the bat, it tells us how far that LSA should be propagated and forwarded. For example, let's start at the bottom right here. An LSA that begins with 4005. That needs to be forwarded throughout the entire autonomous system. And an example of that would be our external route right there. So the external route that's being redistributed into area 67, this is a normal area, backbone area, that LSA type 4005 would be forwarded by the ABR to the backbone, forwarded by this ABR but to this area, and that's what the 4 is all about. The next one is a 2, and the 2 refers to the scope of just the area. It's like what happens in Vegas stays in Vegas. An LSA that begins with a 2, like 2001, 2002, 2003, we should forward that, but only within an area. So for an example, let's say R2 is generating a router LSA for himself. So he sends it here. R4 can forward off to this segment. R5 can forward off to this segment to any neighbors that might happen to be there. But the LSA type 2001 that R4 generates, when R2 sees that, R2 is not going to forward any LSA that begins with a 2 outside of this local area. Again, what happens in Vegas stays in Vegas. That's how far an LSA goes if it begins with a 2. And let's take a look at the last one, 0. What does that imply? 0. And it implies exactly what it is. How far should we forward an LSA that begins with 0? And the answer is 0. You don't forward it anywhere. And the place that comes in handy is, let's say you have a couple networks right here. So I've got a shared network here. I've got 3 interfaces on this area 67, R3, R6, and R7. And if we are using a link LSA, that means it's link, local, and scope. So R6 is going to share information, a 0008 type LSA, and that's just going to describe R6. R6's advertisement of this 0008 link LSA would go something like this. Yeah, it's a good day. My name's R6. I've got this gig 2/0 interface. Currently, I've got these 2 or 3 or 4 IPv6 global addresses associated with it. Thought you might want to know. And it advertises on this link. R3 now knows what interface R6 is using, what IPv6 address is using, and so forth. And R7 and R3 would all do the same. However, any of those LSAs, those link LSAs, R3, when he gets that, he's not going to forward it anywhere. He's just going to say, thanks for the information, I appreciate it, and keep it for his own use. And that's new, by the way, to IPv6's OSPF. We didn't have a link LSA previously. So what have we learned about these wonderful codes? The very first number shows the scope. 0 says don't forward it. 2 says forward the LSA only inside your area, like area 67 or area 0 or area 45. And if it's a 4, it says give it to everybody. That LSA, no matter who generates it, if there's a 4 in front of it, it needs to go to all areas. The backbone, non-backbone, we're going to forward it. All the area border routers are going to forward it right across. Now that we know the first character of these OSPF version 3 LSA types represents the scope of the LSA, let's take a look at the rest of the numbers, which, by the way, 1, 2, 3, 4, 5, and 7 are identical as far as the last digit as they were with IP version 4's OSPF. Now, behind the scenes, they did change some rules, not too significant, so let's take a look at some of the details here. Router LSAs, that's the same. Every router inside of OSPF is going to generate an LSA for itself that describes itself and the various links it has connected to it. A network LSA is going to be generated by a designated router, very much the same as it was in IP version 4's OSPF. The one difference, though, inside the network LSA with IPv6, it doesn't have all the details about the IPv6 layer 3 addresses. Why is that? Well, they did something down here that's going to help with that. They have this new type 2009 that describes intra-area prefixes. That's all the prefixes, all the networks, if you will, that are inside of a given area. So they offloaded the network LSA portion from carrying some of that information. They put it down here in 2009. We'll be down there in a moment. 2003 is the inter-area prefix LSA. It's just a summary advertisement. That's an ABR. And that ABR says, okay, I know the rules. I can't send LSA type 1s between areas because what happens in an area is supposed to stay in an area. So, for example, network 67, the ABR gets it and says, oh, I can't advertise that LSA, but you know what? I can advertise a type 3, or more specifically, a 2003 LSA that goes into this area so that these guys can know about that network. So what used to be called a summary LSA is now called an inter-area prefix LSA, which is perfect. It's a inter-area, meaning between areas. It's talking about a network, a prefix, and it's an LSA type 3. So that's what it's now called. The 5 right here, the 4005, is the external LSA. So it used to be called an AS external. Now it's called the AS external LSA. That's if R8 has the 8888 network. As an example, R7's redistributing that into OSPF as an external type 2. And now that LSA is a type 4005, which, look at the scope. The 4 says, go ahead and just forward it. Now everybody knows about the 888 network. The only problem is the advertising router who sourced it is R7, and Area 0 and Area 45 don't know anything about R7. So to help them out, we also do the 2004, which is the inter-area router LSA. It's effectively the area border router again, advertising another summary, but this time the summary is representing the router in its local area that sourced that route into OSPF, redistributing it, for example, from RIP Next Generation or from some other non-OSPF source. The NSSA LSA is if we are in a stub area and we still want to redistribute in, very similar to as it was in IP version 4's OSPF. And this new one is the link LSA. It's 0 in scope, meaning don't forward it to anybody, but this is how any devices that are connected to each other are going to learn the details about the interfaces of those directly connected neighbors. They'll know the interfaces and any IPv6 addresses connected to those interfaces. It didn't exist previous to OSPF version 3. And then last but not least, we have the intra-area prefix. Inter-area is like between two areas. Intra-area is within an area. And this, my friends, the 2009 is going to describe every single IPv6 prefix inside of a given area. So R3, R6, R7 are all going to have exactly the same link state advertisements in their link state database regarding Area 67. Now, it just so happens R3 is also going to have a copy of a link state database for Area 0, and it's going to match the Area 0 link state database that R1 and R2 have. So every router is responsible for getting and collecting and having an exact copy of the link state advertisements in the link state database as every other router in their respective area. One thing that's helped me quite a bit over the years is actually doing hands-on. So I'm going to encourage you to do the same thing right now. Number one, please download from the Nugget Lab area the topology, or you can just take a screenshot of this. Either way is great, because I found that looking at the topology while I'm configuring at the command line interface is very helpful. And I might even just do check marks like, okay, just do gig 1, gig 1, gig 1, they're all in the same subnet, and then go to R3, R4, R5, and just to visually see it as I configure is very, very helpful. I think it will be for you as well. The second thing I'd like you to do is build the topology. I would like you to put this in place before OSPF is in, because we're going to do that together here in a moment. So pause me if you haven't already put this network together. Pause me and go ahead and put together this topology. As a little bit of insight of how this works, it's basically these gig interfaces are all connected to the same layer 2. So I've got a switch that connects these 3 devices. I've got a switch that connects those 3 devices. I've got a switch that connects those 3 devices. And then I've got a network coming down here, and down here. Those interfaces are all up and active, and I have a connection between R7 and R8. You could go through a switch or crossover cable, it doesn't really matter. But I would absolutely like you to build this topology. Number one, just for the basic practice of working with IPv6, it's going to be huge, because you'll get to troubleshoot it as you put it together, as you do a typo here or what have you there. And then after you have it built, I'd like you to save it and then come back and join me for the rest of this nugget so we can put in the OSPF together. If you're not at a point right now where you can put this topology together, finish the video with me and then come back and you can join me with it again as we work through the OSPF. Also, in the download area for this nugget in this series, in the Nugget Lab area, I'll have the OSPF related configuration for you. So if you want to double check your work as we add OSPF, that information will be there for you as well. So having said that, let's begin our OSPF configuration. I'll walk you through it step by step.